All right. Good morning, everyone. So it looks like almost everyone's here, so we'll get started. Again, I just want to remind you that homework number 2 is due this Thursday, so it's only a little bit over 3 days from now. Okay, so make sure you start as early as possible. Um, yeah, some of the problems you might be finding them challenging, not necessarily very difficult, but they may take a lot of time because the um, complicated processes for the nature of this assignment. Okay, so a lot of them are the similar to the several examples we went in through the class. Okay, for like the ice bring in contact with water, and then what's the final temperature. So it depends on what amount of ice you have um, starting with, and then what amount of water you're starting with. You might end up in different territories. So then, and there's might be like phase transition involved. Okay, so just make sure you get started as early as possible. Also, I want to emphasize that Kayla will be helping you guys either as a tutor or in the SI section tomorrow at 10:20. Okay, so if you want to go to the SI section, make sure you sign up. If nobody signs up, she will not show up. Okay. All right. So today we are going to check on chapter 15 on thermodynamics. We'll also we'll be talking about the laws of thermodynamics and then also be talking about the application of these laws. Okay, so let's take a look here. All right. So the first section in this chapter talks about the first law of thermodynamics. Okay, so this is basically it's starting with the this James Joule's experiment that we showed earlier in the previous chapter. So basically, in this experiment, as we mentioned before, Joule he demonstrated that you can actually convert mechanical work into the heat, which is a form of energy as well. So mechanical work is equivalent to the heat that you can add it to a system. So that means if you are doing, in this case, if you ignore that the heat process here, then you'll see that mechanical work is converted here or added to the system here. So then the system for the water here, the temperature will rise, okay? Which it's equivalent to the putting heat into the water so that the temperature of water will rise, okay? So in this equation here, Q is equal to capital C times delta T. This is another expression for definition for heat capacity. If you use capital C, that means the specific heat capacity of the material as a whole. It's not a small c, which means the heat capacity for the material per kilogram called specific heat capacity. So capital C is just called heat capacity. Small c is called specific heat capacity, and capital C equal to the mass times the small c. Okay, just want to point out that. All right. So basically, from the experiment earlier, you will see that. So if you do work to the system, or if work is added to the system, then the temperature of the system will increase. Okay, so if the temperature of system increase, then we say that internal energy is increased. Okay, so basically the internal energy of a system is directly determined by the temperature of it. Okay, so we call it that U. All right, so delta U means change in internal energy. So change of internal energy of system comes in two forms. You can add the heat into the system directly, or you can make the system do work, or the environment doing work to the system. Okay. So in this expression, if you write WU, change in internal energy equal to Q, the heat added to the system minus the work. Okay, so then this work means the work done by the system to the surroundings, okay, to its surroundings. So W, then it's the work in by the system to the surrounding. Okay, in another textbook, you may be seeing delta U equal to Q plus W. Okay, so then in that case, if this is a plus sign, then that means the work is defined by the work done by the surrounding. Okay, so if you see that, just make sure that you understand that's the definition for work. In that case, is work done by the environment, okay, or the surroundings. But in this textbook, we are using minus sign. That means work is done by the system, okay, to the surrounding. All right. Now, in reality, you might be having like heat being added to the system, and then at the same time, the heat is going out of the system. So, for example, um, one of the exercise we did in the class for our body radiation, right? So our body gives out heat, at the same time our body takes in heat from the environment as well. So then the net heat to our body should be equal to Q incoming minus Q outgoing. Okay. Similarly for work, sometimes you may have the system doing the work to the surrounding, and then at the same time the surrounding is doing work to the system. So then the network should be equal to work out from the system, which means the work done by the system, minus the work in, which means the work done by the surrounding to the system. Okay, so that gives you a network W. All right, but basically change in internal energy should be equal to the net heat change minus the network, okay, done by the system. All right, then this is called the first law of thermodynamics. Okay, so basically it says energy is conserved. Okay, so if you have energy added or that is being or work being done, then that equal to the internal energy change, right? So there's no new energy is being generated here. Okay. All right, so let's take a look on the first example on first law of the thermodynamics. We'll be looking at a dynamic gas system or diatomic gas system here. It says this gas does 300 joules of work and also observes uh, 2.5. Okay, so this is kilojoules. Okay, so make sure you pay attention to the unit here. Kilojoules are heat. What's the change in the internal energy of the gas? Okay, so you'll be looking at the equation we just checked on the previous slide. Okay, so let me just put the equation down here so you can see which equation to use. So you'll be using delta U, which means the internal energy change of the system of the gas equal to Q minus W. Okay. So simply W is 300 joules, and then Q is 2.5. Okay, just in kilo joules. Okay, I think I'll just give you guys 1 minute, and then we'll take a look on the final answer here together. All right, so I think this is a simple exercise here. So the only one thing you want to do is just pay attention to the units, okay? So Q is 2.5 kilojoules. That means you want to multiply by 10 to the third. And minus W is done by the gas, okay? So it says it's the gas does that much of work. So that means minus 300, okay? So that should equal to 2200 joules, okay? So this is the internal energy change of the system, okay? So again, in this chapter, when you refer to a system, okay, so that means most of the time that means a gas system. Okay, so we'll be focusing on the ideal gas or the gas system here in this chapter mainly, unless it's specified as another substance. Okay, all right. So that will be the internal energy. energy change. So Q equal to minus W, or delta U equals Q minus W. Okay. Again, keep in mind Q is the net heat change of the system, and then W is work done by the system. All right. So let me know if you have question. You can unmute yourself and speak up. All right. So if that's clear to you guys, we'll move on here. All right. So as I mentioned earlier, you might have during a heat process, you might have heat come into the system, and then at the same time there might be heat out of the system. Okay, so in this process here, heat comes in, heat goes out, and then at the same time you might have work done by the system to the outside environment, and then the surrounding the environment is doing work to the system as well. So it might be complicated, or might be just a simple process that there's just heat goes out, and then there's just work done by the surrounding to the system. Okay. As long as the change in internal energy is the same, all right, if the system starts out at the same condition, for example, the same temperature, same pressure, same volume, and same amount of the molecules for a gas system. Okay, so then they will end up at the same status as well. Okay, so if the internal energy change is the same. Okay, so for these two, although quite different processes happening on the two systems, but the result will be the same. Okay. For biological bodies, first law of energy thermodynamics also applies here, which means the energy conservation. So, for example, for our body, the change in our internal energy is equal to the heat. Okay, so if this is if our body temperature is higher than the surrounding, then we gives out net heat. Okay, and then if we are doing work, so for example, if you are walking or lifting some loads, etc., then you are doing work to the outside environment. And then if you are eating, okay, some food, so energy then comes in food as well. Okay, so the change in our internal energy of our body is equal to Q minus W. In this case, we have an extra like chemical energy being takes in the food here. Okay, so at that one there. All right. Now for like plants, they takes in heat from the sun, and then there's also like photo synthesis happening at the same time. It will give out heat. Okay. Now most of the time the plants doesn't work. Okay, but change in internal energy, okay, should be equal to Q in minus Q out, okay, and then plus the stored energy in the food, okay, in the plant's body, okay, so etc. So again, first law of thermodynamics applies here, right? Okay, so that's first part of this chapter. Conservation of energy, our first law of thermodynamics. Now let's take a look on the application of this. Okay, so this figure shows you the first one of the first like engines built after the discovery of the first law of thermodynamics. Okay, so that's only like about 60 years after it was first discovered. That was a pretty fast process to put into industrialized use. Okay, so basically, this is the first law of thermodynamics, right? So the heat comes in is equal to heat gives out minus W, which means in the process here. Okay, so this is a heat engine. What it does is it takes in heat, and then it does the work, and then it dumps the heat out to the environment. Okay, so for a heat engine, it operates in cycles. So for each cycle, it starts the same condition as initially. So then that means for each cycle to complete it, it will return to the initial condition, right? So then the change in its internal energy will be equal to 0, right? So in that case, delta U is equal to Q in minus QW. That gives you net Q, okay? Net of Q, and then minus W, right? So if this is equal to 0, delta U is equal to 0, okay? So then Q in minus Q out, or Q out here, that should be equal to W, right? So that should be equal. So that means W is equal to Q in minus Q out, okay? So that's where this equation is from, okay? So this is basically from the first law of thermodynamics, okay? So for a heat engine, that is to go that way. All right. Now, this is the heat engine. That's the simple illustration of how it works, okay? Now, some people, they were thinking about if you can convert all the heat takes into the work done, then this engine will have a very high efficiency, okay? But in reality, that's not possible, okay? So in reality, you have to have some excess heat dumped into the environment. So that's also called the second law of thermodynamics, which we'll talk about this more in the coming section. But this is just one of the note I want to give it to you guys. Okay, so in reality, for any engine that you can design, you cannot take convert all the heat takes in to work totally. So that means you have efficiency of 100%. That's not possible. Okay. All right. So the most common engine you guys might not see directly, but you use it directly, maybe very often, or if not in a daily basis. So it's the engine in our car. It's the cylinder engine in our car. So how the engine works in a car is this. So it takes fuels in here and then mixture with air. Okay. So then the mixture of gasoline and air will be ignited. Then there's chemical reaction happens here, release a lot of heat, okay? So then the gas system here in the cylinder here takes in the heat from the chemical reaction of combustion of the gasoline, right? So that's the form of heat takes in here, and it will increase the temperature of the gas system and also pressure. So then it will push the piston here, which means the gas system is doing the work, okay? And then the work is being transferred by very complicated like engines over here, connecting to the wheels, etc., doing work, okay, to the car, the whole body. And after that is done, the excess heat will be dumped out, okay, from your exhausted pipe to the surrounding. Okay, so that's the full process of engine in your car. Okay, so that's the process there. All right. In this section, we are also going to take a look on several thermal processes. Okay, that is can be used in the process of exploring the complicated other thermal processes. Okay, so we'll be starting with these ones called quasi static processes, which means we are assuming that these processes happen very slowly. So then there will be uniform temperature and pressure throughout all region of the system. Okay. Now, in reality, you are mostly experienced like in one spot of the system has higher temperature and pressure, and then the other spot is having less temperature and process and pressure. Because of the process, the heat transfer takes some time to distribute thoroughly out. Okay, but we are going to assume these ones simple processes here, and then take a look on the details of them. So that in the future, in coming sections, we can apply these ones to the more complicated processes. Okay. All right. So the first simple process we are going to take a look is the so-called this process that is constant pressure process throughout. Okay, it's so-called the isobaric process. Okay, so and then the second one we'll be looking at is the volume is being constant, and it's called isochloric process. The third one we'll be looking at is when the temperature is constant. It's called isothermal process. And then the last one we'll be looking at is the no heat transfer process, or called adiabatic process. Okay, so we'll take a look at them one by one here. So the first one we are going to be focusing on a constant pressure process. So for example, if you have a gas system here in this piston over here, now we are assuming that this piston can move up and down without friction with the wall. Okay, so if the pressure inside the gas is constant, right? So for example, for the expansion of this, if you add heat here, if you let this piston move freely without friction, so then the pressure here is constant, right? Because the pressure here will be equal to the weight of the piston divided by the area underneath the piston. So mg divided by A, that's constant. Okay, it's equal to the pressure inside the gas system. Okay, so if you add heat into the system, this will expand. All right. So then if you look at the it's PV diagram, which means you plot P versus V, right? Now you can see P is constant here, so that means straight line here. Now V expand, V goes from small v to larger V. All right, so this is a process called constant pressure or isobaric process. Now in this case, you can see in the process, it takes in heat, but at the same time, the system is doing work to the surrounding the piston over here, right? So how much work is done by the system to the piston? So we'll have to look at the force by the gas system on the piston, which is called F, right? F equal to pressure times area. According to the definition for pressure, it's equal to F divided by A, then F is equal to P times A, okay? So this is how much force is being done. And then times the distance D, that is the piston moves about distance D over here. So F times D will be the work done by the gas system, okay, or work of out. That's equal to F times D. Again, F equal to P times A, so then that equals to P times A times D, all right? Now A times D will be the cross-sectional area times the distance over here. So that's equal to the amount of the expansion of the gas system, right? It expand by that amount in volume. So work done by the gas system then is equal to the pressure times the change in volume, delta V, all right? Which if you look on the graph over here, it's exactly the rectangular area here. And this is equal to the area underneath this curve from A to B under the PV curve, okay? So in that sense, if you have a PV curve for, or PV, or called PV diagram for the gas system, then you can calculate how much work is done by the gas system to the outside surrounding by calculating the area underneath the curve from point A to B. Okay. Now we can do this conclusion by looking at the simple process of P is constant. All right. So we will take a look on one example, and then we'll move on to the next slide, which is about in general, your P might not be in as a constant. Or let me take a look if I remember that correct. Let's take a look on here first. So in general, if you go from A to B under a PV diagram, okay, you might have change in pressure, all right? But you can divide that process into very small pieces of rectangular shape of small processes, right? That will give you a pretty good approximation of what is work done by the gas, okay? So in that case, this is if you have learned calculus, you realize this is how the calculus is being done. It's actually dividing into small pieces, okay? Delta V, which you set delta V to be very equal to 0 or very approximately approaching 0. So then you can see from each of rectangular area here, above here, pressure is not changing, right? So in each of this small rectangular shape here, the pressure is constant. So then you can apply the conclusion we got from the previous a couple slides back there. The work done by the gas system should be equal to the area underneath, okay? Then you add them all up. So then it's, again, even if you have a pressure that is changing, then the work done is still the area underneath the curve from process, say from A to B or from B to A. Okay, either way, depending on which is your starting point. Okay, all right. So let's go back to the example here. This is a isobaric expansion of water. Okay, so in this case, you have a system of water. Okay, it says 1 gram of water is placed in a cylinder and the pressure is maintained by 2.0 times 10 to the fifth Pascal. So usually you can maintain the pressure by having the piston that can freely move without friction with the wall. Okay, so that's the same case over here. It says the temperature of water is raised by 31 degrees. The water is in the liquid phase and expand by the small amount of 1.0 times 10 to the minus 8 meters cube. Find the work done and the change in the internal energy. Okay, so what you are looking for here, you are looking for work done, and then what's the change in internal energy. All right. So this is isobaric process. So you can use work done equal to P times delta V. Okay. And then internal energy change should be equal to Q minus W. All right. You need to look up the specific heat capacity of water here, okay? Because heat given to the water, that should be equal to MC delta T. It gives you delta T, but C is not given. So let me just write C here. C is 4186 joules per kilogram times degrees Celsius, okay? I'll give you guys a few minutes to work on this example, and then we can take a look on the solution together afterward, okay? And if you have your answers, you can click on the top of the slide here and then submit your responses, okay? You do have to open the PowerPoint slide on your end to do that, okay? All right. So let's take a look here. I see some response in there, but let's take a look. Okay. So A here, you're going to do, because this is isobaric process. So remember, you can use this only on this is isobaric process. Okay. P is constant. All right. Otherwise, you may be looking at a different formula, but this is for isobaric process. So work is equal to P times delta V. In this case, it tells you that P is equal to stay at constant 2.0 times 10 to the fifth Pascal. And then the volume expanded by 1.0 times 10 to the minus 8 meters to the cube. They are both in SI units, okay? So then the work done by the water to the surrounding should be 2.0 times 10 to the minus 3 joules, okay? It's a very small amount because the expansion is very, very small, okay? So yeah, so this is a liquid. Now, if for gas, then expansion could be more. All right, so that's part A there. Part B, we are looking for delta U equals to Q minus W, right? W is what you calculate there, but Q is equal to M times C times delta T, all right? Minus W. I think we have M, then C is this guy, delta T is also given, so we can do that. So it tells you 1 grams of water, right? So 1 G, so that means 1 times 10 to the minus 3 kg, okay? So pay attention to the units here. Multiply by 4186 joules kg times degrees Celsius times delta T is being 31 degrees Celsius. Okay. Minus 2.0 times 10 to the minus 3 joules. Okay. So that will give you roughly 129.764 joules, or if you just keep two sig figures, it's 1.3 times 10 to the 2 joules. Okay, about that, about roughly 130 joules. Okay, I see one of you guys got like 129.764. You probably didn't do the conversion for the mass. Okay, but otherwise you got, I think you got the rest of the work right. Okay. Any questions you guys might have? Can unmute yourself and let me know. Okay. All right. There's a question in the chat. Yeah. So as I said, it's safe to always convert to the SI unit and then get the answer. And then if the question specific asks you answer in certain unit other than SI unit, you can convert to that unit that is mentioned. But sometimes, for example, if sometimes you might be seeing like the C is given as not joules, so say 4.186 joules per grams degree Celsius. So this is, you might see this in some cases. This is we call like CGS units, centimeter grams system units. Okay, so in that case, you are given 4.186 joules per G times per gram times degree Celsius. In that case, you want to have your M as just as 1 gram. You don't have to convert because M times C, then gram and gram down here, they are consistent and can cancel out. Okay. So again, but it's always safe again to just use SI unit. That means you want to convert this to SI unit and then this as well. Okay. So if you did that twice, they cancel out. The operations will cancel out. Okay. But yeah, it's always safe to do that. But just be careful about what's given. And then sometimes you might need to convert the units. Okay. All right. Any other questions you guys might have before we move on? All right, if you are clear, I guess we can move on now. So we talk about, so even it's P is changing, you can also calculate the area underneath the curve. But in this case, you can see it's not simply P times delta V. Okay, so there's other mathematics that have to be done in that case. All right, but we are going to move on to the second process here. Or another, yeah, the second one, I think that's right. So in the case that volume is not changing, so it's called constant volume process or isochloric process. Okay, so in this case, if you have a enclosed, say, container here, now this is probably like a glass window here, you can see what's going on inside, but this is the fill up to the top here, and then it's closed here. So then if even you add heat into the system, the volume will stay the same. All right. In that case, probably other parameter will change. Okay. So in that process, the work done by the system over here to the surrounding, because the volume is not expanding, so then the gas or whatever liquid inside couldn't do work to the surrounding, right? Because it couldn't push against the surrounding. So then delta V will be 0. So work done by the system will be equal to 0. Okay, so that's constant process. So in this case, probably the pressure will increase and then the temperature will increase as well. But on the PV group diagram, we will only see pressure increase. Okay. All right. Now, in reality, okay, so you might have combination of, say, constant pressure process and then constant volume process. For example, if you go from A to B to C to D, or from A to B to C, so then this is from A to B, this is constant pressure. From B to C, this is constant volume. Okay. Now that would be equivalent from going from A to D to C. All right. So in that case, you can calculate like the volume underneath the curve here, right? If you go from A to B to C, all right, then the volume underneath the curve from A to B will be this larger rectangular, right? And if you go from A to D to C, then the volume underneath will be from this small rectangular, all right? So then for the gas system to go like one full circle here, so from A, P, or actually here, from A to B to D to C to D back to A here, okay? Then there's a net change in area over here, which is equal to this guy, all right? So then for this cyclic process, that means return to the initial status. Okay, so called cyclic process. So then the area enclosed by the process will be the net work done by the system to the outside surrounding. Okay. Now, in general, you might have, say, changing pressure or changing volume. So you might have like a process, cyclic process like this. Okay, so it goes back to the initial starting point. So then in this case, this area enclosed by the process is also equal to the work done by the system to the outside surrounding. Okay, so from the PV diagram, that's how you can figure out what's the work done by the system to the surrounding. Okay. All right. The third process is called isothermal process. That is when T is constant. All right. So when T is constant for the same gas system, then for if this is just one same gas system we are talking about, then the number of molecules stays the same. So T is the same, N is also the same. All right. So then from the ideal gas law, PV equal to nRT, if you move V to the other side, then P equal to nRT times 1 over V. Okay. In that process, then P is inversely proportional to V. If you plot P versus V, that's called the PV diagram. So P versus V, then at different temperature, you are going to see a parabola curve. Okay, so this is the 900K curve. This is 700, this is 500, 300, but they are all parabola parabolic curves, right? So if that's the case, then if you are going from, say, let's pick a P here. So for example, like 700 maybe K. So then this is the curve there. So if you go from initial point VI to final point VF, so then the area underneath this parabolic curve would be the work done by the gas system to the outside surrounding, okay? Now, mathematically, you can prove that this work done under a parabola curve is equal to NKT line of VI over VF, okay? So V final divided by V initial, okay? Now, this is most easily done with the knowledge of calculus. So basically, if you are doing calculus, if you integrate from initial position to final position, then it'll give you the area underneath that curve. Okay, but because this is not a calculus based class, I'm not going to show you the work. Okay, but this is the result. Okay, so this can be mathematically proven. So work done for an isothermal process is equal to NKT ln of V final over V initial. Okay, or equal to nRT ln of V final over V initial. Okay, so either way. So I have mentioned this earlier, like the internal energy of the gas system is defined just by the temperature, okay? It's not defined by the volume. So this is the case. This is a simple demonstration. You can prove that this is just internal energy is just equal to the is determined by the temperature. So if you have ideal gas here, now if there's a valve here, if this is vacuum on the other side, which is the same volume as this side, so pretty like mirror image of the shape of the left side here gives you this right hand side shape over here. So if you open the volume, you'll see that this is going to expand to the vacuum side, right? Now, the internal energy of the system will not change even during this process because this is the vacuum here, right? So when this is expanding over to the vacuum side, it's not pushing against anything, right? So it's vacuum, it just go there freely. So then in that sense, there's no external work done being done there. So the temperature will stay the same, right? So you can see volume change, but temperature stays the same. Then the internal energy of the system, gas system still remain the same because there's no added heat into the system. Okay, so U here is going to be still the same. Delta U is still equal to 0 in this case. Okay. All right. We will take a look on the example here. It says a monatomic ideal gas initially at 20 degrees Celsius and 200 kpt, kilopascal, kPa, has a volume of 4.00 liters. It undergoes a quasi-static isothermal expansion until its pressure reduced to 100 kilopascal. Find the work done by the gas and the heat absorbed by the gas during the process. Okay. So in this case, we learn for isothermal process, work is equal to NKT, right? Let me see, just the capital NKT, natural logarithm of final volume divided by initial volume, or small n RT, the same here. So either way, okay. Now this is ideal gas, okay. So this is one equation you can use, either this format or that format. For ideal gas, is equal to PV equal to NKT, right? Or PV equal to nRT. So this is based on ideal gas. So when you see ideal gas in a problem in a thermodynamic, always remember this equation, okay? You might use this equation for ideal gas, as always. Now for work done, we learned this already here. So let me see what else do you need here. You might also need the first law of thermodynamics, delta U equals to Q minus W, okay? Because in A, you're looking for W. W equals to what? That's A is looking for, and B, you're looking for Q. What's Q equal to? All right, so I think you are going to use those three equations, all right, for this problem. I'm going to give you guys a couple minutes to maybe start working on this. And if you would be able to finish that with an answer, you can also submit your responses online. Okay, but I'm going to give you a couple minutes here. All right, so as time is running out, we are going to just look at the solution together on this one here. So I'm going to just use a new paper here on this. All right, so as I mentioned, A, I want to consider W equal to NKT line of V final over V initial, okay? We don't know N, we don't know, we do know K, we do know T, I think, but we do not N here, right? So what do we do here? As I say, you can use PV equal to NKT, right? So it also tells us PV, so you have to be very creative here. So NKT, you may treat them as one term that can be calculated by P times V, all right? So PV equal to NKT. So then this is also equal to PV line of V final over V initial, okay? So on this one, and then let me pull up the equation problem here to see what's also given. All right, so in this case, initial of Vi is given, not final of, so this is Vi initial, okay? P initial, V initial, line of V final, P final. It says, so the volume expanded, okay? So then N stays the same, K is the constant, T is the constant. So that means P times V is equal to constant, right? Or that means PI VI is equal to PF VF. Okay. So in that case, then you can actually rearrange the terms and you can see what's VF over VI, because that's what you're looking for in the parenthesis here in the argument of the natural logarithm there. So you can do both sides divided by VI, right? To get rid of VI there, and then both sides divided by PF. PF there to get rid of PF there. So basically this tells you PI over PF then equals to VF over VI. Okay. So on this one, you do have to be creative about solving for the problem here. So then takes that in there. So that W is equal to P initial given V initial natural logarithm of P initial over P final, okay? Because it gives out P initial, V initial, and P final, okay? So then now you can plug in the numbers you have into the equations. So P initial is 200 K Pascal. So K means 10 to the third. V initial is 4.00 liters. That means 10 to the minus 3 meters cube. Okay. Lawing of P final, or P initial here, 200 times 10 to the third Pascal divided by P final given as 100 times 10 to the third Pascal. Okay. So then this will give you 555 joules as the work done by the gas to the surrounding. Okay. So this is part A. Part B is asking you the heat absorbed by the gas during the process. So you're looking for Q, and as I mentioned, you're now going to use delta U equals to Q minus omega, right? So what's delta U here? For a isothermal process, because delta U is equal to like 3/2 of nRT, right? So if delta T is equal to 0, which means isothermal, right? Isothermal process. So then your delta U is going to be equal to 0. Delta U is equal to 0. So that means Q is going to be equal to W, right? Equal to 555 joules. Okay. So again, just remember, if this is an isothermal process for an ideal gas, then its change in internal energy is equal to 0. Okay, for an isothermal process. Okay. All right. Let me know if you have questions on this. So if you are clear, the last process here is called adiabatic process. Okay, so no heat process. So that means Q is equal to 0. Okay. Now you can achieve this in two ways. One way is to have the system isolated. Okay, so well isolated. Okay. So for example, like this isolation, put a lot of isolation to the system. Then in the process, whatever happens, the Q is equal to 0. Okay. Either in this way, compression of the system or expansion of the system. Okay. On the other hand, you can do a adiabatic process, like you might have not have the perfect installation here, but if you can do the process so well, quickly enough, okay, so quickly enough, so then there's no time for heat to escape. So then also Q is equal to 0. So in this case, okay, so according to delta U equal to Q minus W, okay, so process happens very fast. This is 0. Now, in the process here, you are doing work to the gas system. So this is greater, this is actually less than 0 because it's the surrounding doing work to the gas. So then your delta EU will be equal to minus Q, which will be greater than 0, all right? So if delta U is greater than 0, then delta U equals to like 3/2 of nRT. So then T will increase, all right? So if you can do this so quickly, so there will be increase in temperature very quickly. Okay, so this is one of the demo we can do in the class, or if you're in lab, I can show you in the lab here. So if you do this quickly, just put a piece of paper there, it will ignite the paper. All right, or you can also find this on online for a demo. Now, for diesel engine, it actually does this. Okay, for like the usual car gasoline engine, you have there's a ignition mechanism, but for diesel engine, it doesn't. It just happens quickly, so then ignite the combustion. Okay, there. All right, so this is the adiabatic process. To summarize, for those four processes, what you have is for constant pressure, W is equal to P times delta V. Constant volume, that means W equal to 0. And constant temperature, that means delta U equal to 0 or Q equal to W. Okay, for adiabatic process, Q equal to 0. Okay, and I think I'm going to stop here, and then next time we'll be checking on the second law of thermodynamics. Okay, so we'll stop here for today, and I'll see you guys on Wednesday. All right, see you guys.